Welcome to module 49 of Database Management Systems course in the IIT Madras online BSc program. We have been discussing about transactions, particularly serializability, recoverability and so on. On that we had seen that a database can be recovered to a consistent state from an inconsistent state due to failure by cascaded or cascadeless rollback. And we have also discussed about view serializability as a weaker serializability condition for better concurrency. However, testing for it is NP complete. So, we saw some heuristic methods of checking for it. Now, moving forward, what you are left with using conflict or view serializability and recoverability may not be adequately concurrent schedules. So, we need to manage the concurrency, control the concurrency through the design of the schedule. You cannot just predict that beforehand that this is the schedule which is best, but can we make it so that the schedule as it goes would be able to take concurrency as and when it comes, while maintaining all the acid properties and also ensuring fair amount of recoverability. And that is what leads us to locking mechanism or the lock based protocols, as we will see. So, concurrency control, if we look at that, there has to be a mechanism that will ensure that all possible schedules are both conflict serializable, because that can be tested in polynomial time, and recoverable, preferably cascadeless recoverable. Right? So, this can be ensured by a policy that once transaction executes at a time, which will always give serial schedules, but it will have a very poor degree of concurrency, very bad throughput. So, the concurrency control schemes trade off somehow dynamically the amount of concurrency they will allow and the amount of overhead that you incur for that. For example, testing a schedule for serializability after it has executed is certainly too late. I mean, it does not help. So, the goal that we are going to pursue is to develop concurrency control protocols that will assure serializability, not pre-designed ones. Now, one way to do that, and I am sure you have come across this idea when you did operating system in a little different way, maybe in terms of semaphores and critical sections and stuff like that, is similar, that one way to ensure isolation. What is the basic violation of isolation? That the same data item, if it is touched by two transactions at the same time, then the updates to that may be conflicting. Right? So, what if I can guarantee that a data item will always be accessed in a mutually exclusive manner, so that when one is making a change, the other should not be allowed to make a change. Now, naturally, you can enforce that to hold a lock on the entire database. It's transaction 1 is working, nobody can work on that database. That will again lead to strict serial schedules, but very poor performance. So, we would like to associate locks specifically with data items, and that is the basic idea, to provide exclusive access mechanism. And this whole gamut of strategies which let you do this is called the lock based protocol. So, what do you do in the lock based protocol? A lock is a mechanism which controls the concurrent access to a data item. Right? So, you can lock a data item in two ways. I mean, that is in general. I mean, there are several kinds of locks which has several other modes, but the simplest form is two modes. What is that? One is exclusive and another is shared. In the exclusive mode, if you hold a lock in the exclusive mode, you can both read as well as write, read as well as write. And we normally use xlock command to request to have a using a lockx instruction. I will say lockx data item to get a xlock, that is exclusive lock. I can do read write both. The other is a shared lock where I can only read. See, two transactions cannot write at the same time, or it is also not possible that one is writing, another is reading. The data may be inconsistent, as because you may read before the write or you may read after the write. But two transactions or more can read from the same data item at the same time. So, they can share, and more often you read. So, you have a S lock which you can get by using the lock S instruction. Now, once you have a lock, you have to explicitly provide unlock on that data item to remove that lock. Otherwise, others will not be able to do anything. So, these are made by the concurrency control manager. So, a transaction always have to request, and they will be able to proceed only if it has got its lock request granted. So, we talk about lock compatibility matrix. For example, what kind of locks can be held at the same time. So, if you look at the lowered one, a shared lock can be held along with a shared lock, because you can read, multiple transactions can read from it. But certainly, a shared lock cannot be held with an exclusive lock. That is, you cannot read when somebody is trying to write, or vice versa, or two people cannot write. So, this is yes, but these three are incompatible. So, which means that at a time any exclusive lock can be held on a data item by only one transaction, whereas a shared lock can be held by multiple transactions. Now, naturally, when you include unlock, since you are unlocking, removing this, it does not matter what is the lock that is already held on that data item. It can do for shared as well as for exclusive. So, what is a lock based protocol? That you request for or granting of a lock to the lock manager. So, transaction request for it, and if that lock can be given, the transaction will be given the lock. So, for a shared one, for sharing a lock, any number of transaction can hold the shared lock, but if any one transaction holds an exclusive lock, then no other transaction can hold any lock on that. So, under such cases, you have to wait for the lock till all shared locks or the exclusive lock has been released by the respective transaction. You have to hold on to the lock as long as you want to access the item, otherwise the whole protocol will be violated. And once you are done, so then you must unlock that data item, but there is a caveat to it. It is not necessarily always desirable, we will see why, that you release the lock on a data item as soon as you are done with that data item, because there may be some other logical conditions prevalent with other data items as well. But these are the basic actions. You can request, get a grant, you can share a shared lock. If you do not get a request granted, you have to wait for the lock. Once you get, you have to hold on to the lock and then finally unlock or release the lock. So, here is an example. So, these are two accounts being accessed by two transactions A and B. Transaction A transfers $50, transaction B prints the value A plus B, right. So, it locks B, reads B, deducts 50, writes B, unlocks B, right. So, during that time nobody can touch B, which is what we wanted to do. Similarly, lock A, read A, increment by 50, add 50, write back, unlock, nobody can touch. And what this does, this has to print the value of A plus B. So, it is not going to change. So, it uses a shared lock, reads, unlocks, shared lock to read B, unlock, display the value. If you execute them serially, either as T1 followed by T2 or T2 followed by T1, you will always get the correct value of 300. If you do T1 followed by T2, then you will have 150 plus 150. If you do before T2 first and then T1, you will have 100 plus 200. In both cases, the result will be 300, which is correct. Right. Now, let us see what will happen in terms of concurrency. Suppose we make this concurrent. So, what we do is in T1 we have up to this much here, and then we have T2 here, and then again we have the remaining part of T1 here, right. And we are following the protocol strictly. Before reading and changing, it has taken an exclusive lock, read, computed, changed, and then unlocked because it is done. Similarly, it has done the same for A, you have seen this works, but in spite of that, what will this print? Since it will get the lock on A easily because T1 has not done anything with it, it reads, unlocks A, that is fine. Now, when it asks for lock on B, since T1 has already unlocked B, it will get this shared lock, and it will be able to read that value of B, which is 50 less, which is the final value, true. But just think about it, the value of A that it has will get changed in future. So, at this point, if you remember the color diagram, we had shown couple of modules back of green, yellow and red. At this point, the database is in inconsistent, transitly inconsistent state, and because this B has been unlocked, transaction T2 can read it here, and what it will display quite naturally is 250, 100 plus 150. Whereas, at the end here, when you reach here, the database is inconsistent because it is back to 300, but this transaction will show a wrong value. So, that is what I meant, that though you should release the lock as soon as, at the earliest as you can, but you have to be careful in terms of the logic. Here you are not doing anything with B, but the point is, if you allow someone else to read this B before you have taken care of the A, there will be inconsistency reflected in that transaction. So, this is a bad way of doing that transaction. So, I am sorry. So, what we should do is this, instead of unlock B here, we should unlock B here. What will happen if we unlock B here? If we unlock B here, then this has been done, write has been done, you are still holding the lock on B. This will hold a shared lock on A, it will read A, unlock A, it will try to hold a shared lock on B. So, it has T2 has read A in a concurrent fashion, it tries to hold a shared lock to read B, but the lock is held here exclusively. So, it cannot get it, it will have to wait, T2 has to wait, and since it has released lock A already, you will be able to get this unlock A. I am sorry, you will be able to get this exclusive lock on A. T1 would be able to get that and T1 can proceed. T1 releases. Then finally, when it releases B, the lock on B, only then T2 will get it. So, T2 has been waiting here, and after this T2 will again be able to proceed where you are back to a consistent state. Right? So, when you do this in terms of T3, T4 here, you get a consistent result, and this needs quite a bit of logical thinking for the transaction writer to make sure that even though it does not appear to be necessary, but because of what other transactions could do, you will have to delay the unlock of this particular data item. Right. Now, log based, so this is that is how to use a log based protocol. Now, log based protocols can land you in other problems. For example, think about here, you have an exclusive lock X, you have a shared lock SA, you have got that. So, now at this point you need an exclusive lock here, right, because now you have known that well, as soon as you are done you should not release that lock. So, you are trying to hold on to the lock. So, unlocks are all at the end. So, T3 holds the lock on B exclusive, T4 holds the lock on A which is shared, then T3 can go up to this when it needs an exclusive lock on A, it cannot get because T4 has a shared lock on it, they are not compatible. So, it will have to wait here. T4 needs a shared lock on B to be able to read that value, it cannot get because it is T3 is locked it here. So, it has to. So, both these transactions will wait at these respective points with no resolution. T3 will wait on the lock on A to be released, but that can be done only if T4 gets the lock on B, which can be obtained only if T3 releases the lock on B, which will happen only if T3 gets the lock on A, right, circular logic. So, this will none of the transactions will be able to work, this is called deadlock. So, very similar to the deadlock in operating system. Right. So, somehow one of the transactions will have to be thrown back, rolled back, locks released, so that the deadlock can be broken. So, deadlock is a basic problem of this log based protocols, but still we would prefer it because we have two conflicting requirements now. Either if we do not ensure the isolation through the locks, we can potentially get into inconsistent state. If you try to ensure through the locks, then deadlock may happen. Now, out of these two things, deadlock is an evil, but deadlock is still preferable because we can still undo or roll back certain transactions, get out of the deadlock and try it again. But if the database gets into inconsistent state, then there are effects in the real world which we have no way to roll back. Right? So, we would try to see how these possibilities of rollback can be minimized. So, one way of doing that is to follow what is called a two-phase protocol. So far we are saying that you need a data item, you take it. You are done with the data item, sometime you release it. But no, here we are saying that a transaction a schedule will be conflict serializable, provided the transactions therein follow a two-phase locking protocol, in that in the growing phase the transaction may obtain locks, but it does not release any lock, and in the shrinking phase it may release locks, but may not obtain any lock. If it follows this discipline, then this protocol will assure serializability. Right? So, that is a nice property. Right? So, any schedule which follows the two-phase locking protocol is conflict serializable, but the reverse is not true. There can be conflict serializable schedule that cannot be obtained by two-phase locking, right. But if we do not have enough data, we will have to go with this. Now, in many cases the two-phase locking is actually extended in the growing phase as well as in the shrinking phase by including conversion. This too we talked about, that it can acquire a lock. So, it can acquire an S lock, it can acquire a X lock, or it can convert an S lock to a X lock, which is upgrade. Right? So, instead of releasing it, you are holding an S lock, shared lock, you request for an upgrade to a exclusive lock. So, if nobody else is holding a shared lock on that, you will be given that. If somebody else is also holding, then you will not be given. So, this is also what you can do in the growing phase. Similarly, in the shrinking phase, you release the S lock, you release the exclusive lock, or you convert a exclusive lock to a shared lock. So, in the exclusive lock, you had just alone holding the lock, you downgrade that to a shared lock, so that others can also hold shared lock, and that this protocol assures serializability, and but certainly the programmer will have to finally insert the different locking instructions. So, another alternative that many systems actually support the programmer with is by automatic acquisition of locks. And because that if you have to read, then you need a shared lock. So, why do you tell the programmer to get it? You can just get that. So, the operation says that read will be, if the transaction has a lock on this item, then read it. If it is, then wait till no other transaction has exclusive lock on it. The others may have shared lock because they are going to read. Then TI will be granted a lock S and then you read it. So, you just write read, this will happen in the background to ensure the isolation. Similarly, for write, it is a little bit more complex, but very intuitive. For write, you need an exclusive lock. If you have that, go ahead and write. If you do not, you have to wait until no one else has any lock, because you are going to write. So, you are going to ask for exclusive lock. Right? Now, if you are the only person, this transaction Ti is the only transaction which has a shared lock, then you will request for an upgrade. If not, then you will request for a grant of the exclusive lock. These are just enumerating the possibilities, so that before you write, you necessarily hold a exclusive lock. Before you read, you necessarily hold a shared lock, and you relieve the programmer from the burden of putting it at every place. Right? So, two-phase locking does not ensure the freedom from deadlocks. You can see the transactions here, they are doing two-phase locking because they are only locking, they are only locking. So, both are in the growing phase, right, before they have their shrinking phase, but this will also be a deadlock, because this will be granted, this will be granted, this will wait for this and this will wait for this. Okay. So, you will have a deadlock again. Right. So, it does not guarantee that. Actually, when you make transactions wait for an exclusive lock, then many transactions may be waiting. So, you will have to give it to someone and roll back others or keep them waiting. So, it is possible that a particular transaction may not get the lock it is requesting for a long time, even though there may be several instances. This is not deadlock, because several others have got, but it is just that your turn is not coming. Right? So, that is called starvation. In a loose sense, it is also referred to as life lock. This is something which exists in operating system again, and these kind of things can also happen with the locking protocol. And so, the potential of deadlock exists in all locking protocols, and when a deadlock happens, you will have to roll back one or more transactions, and when that happens, obviously there is a possibility of a cascading rollback. This particular example will show you that. Study it, I will not go through each and every. Study it, you will be able to see it very clearly. Now, there are ways to avoid cascading rollback, which is known as a strict two-phase protocol. We just discussed the two-phase protocol. There is a strict two-phase protocol, which say that a transaction must hold all its exclusive locks till it commits or aborts. This will guarantee that you do not have cascading. I mean, if you have if you can close your eyes and see what cascading rollback is doing, you will understand that, because if you are holding on, others are not being able to work on that. So, if they are not able to work on that, there may not be transactions which have already done partial work and needs a cascading rollback. There is a rigorous one where all locks, not only exclusive ones, but all locks are held till the commit or abort has happened. Right? In this protocol, transactions can be serialized in the order in which they commit. Right? So, these are different protocols. I mean, you do not have to really work through each one of them in detail, but just know that these exist. It is important to understand the two-phase protocol and be able to solve problems with the two-phase protocol. And certainly, one point has to be always kept in mind, that the more and more strict you get in terms of the locking protocol, you ensure safer rollback and so on, but certainly your concurrency is going down. Right? You know, this is just a direct trade off. It's very easy to see, because you are the more strict locking protocol you have, you hold the locks on data items for a longer period. The longer you hold that lock on data items, naturally the option for other transactions to work with those data items become less, concurrency goes down. That is a simple. Now, in terms of implementation of locking, I mean, I just included that because, but it is very simple, straightforward. So, you have a lock manager which manages this, and it is done in terms of a lock table. So, all that you will need is for every data item, you need to remember what are the transactions that are holding locks, what are the types of locks, and who are the transactions that are waiting for locked requests. So, that is a simple linked list data structure which does that. So, it says these are the, this is what is, these are the different ones, this is what has been granted, these dark blue are granted, and this is, so this must be a shared lock. So, and the light blue is waiting. So, this is shared lock, multiple people can access. This is a obviously an exclusive lock, because one is holding it, but still someone else is waiting and so on. So, you just keep on updating this data structure, the lock manager, and using this lock table, the lock manager can easily manage. Of course, I mean, how do you do it efficiently when you have a large number of data items and large number of transactions is of course a good challenge in algorithm and data structure design, but in principle it is quite easy to do that. You will also have to have references in some other way. For example, if a transaction aborts, or if you want to have to roll back a transaction, then you need to, this is looks like more like going by data item wise, but that may not be enough. If you have to say roll back transaction T8, you need to know that these are the two locks already granted to it. So, there has to be other form of reference also available in the lock manager for doing such tasks. Okay. So, we come to the end of this module. Thank you very much for your attention. We have discussed quite a bit in terms of the locking protocol and the primary evil that it creates, the deadlock, right. So, we will have to take little bit more head on with the deadlock in the next module. See you then.